So here we go. We're going to go into the Flyback grid tie inverter simplified schematic discussion. Before we get started, I just want to go over one item, which is the mode of operation, the switch mode of operation. We are operating in this project in a discontinuous conduction mode, meaning if if this is inductor current, okay, and it could be a single inductor, it could be inductance in a transformer, any inductor current that's being controlled by a switch, okay. In our case, when the switch is on and it's closed, the inductor current rises until the switch turns off, and then the current falls till it reaches zero. And then it stays at zero for a while before the next cycle. And this is known as a discontinuous conduction mode. The other two are boundary conduction mode, BCM, which is current rises and then falls to zero and then immediately rises again. So there's no dwell time at zero. And then finally, for continuous conduction mode, the current never reaches zero. So inductor is current is always flowing, but never goes to zero. So those are the three modes, and we're in DCM mode for this project. Now let's go over the elements of what makes this up. So we have a MOSFET switch, which contains an intrinsic drain capacitance. We have an RCD snubber, which is a resistor capacitor diode. We have a flyback transformer, which consists of a primary winding, a secondary winding, and a leakage inductance, which we'll talk about in a minute. The output, it has a diode, a rectifying diode. It has an output capacitor. It has a smoothing inductor, and then an unfolding bridge, which is made up of 4 switches. In this case, we use MOSFETs, and they switch alternately. So, for instance, for the blue side cycle, okay, Q2 and Q5 conduct, so it allows the blue cycle to come out. Then they shut off, and then the red cycle, Q4 and Q3, turn on, but in the opposite direction, so that it now goes negative. So you get a full sine wave from this, and that's why they call it unfolding. And then it goes, we do some voltage sensing, current sensing. We have a relay that controls when we connect to the grid. So those are the elements. So let's talk about how it actually works. So on the PWM side, you have PWM signal being modulated by this half sign. So on any given piece of pulse here, so when this pulse rises and goes high, it turns on the MOSFET. When the MOSFET turns on, current flows from V in through the primary, through the leakage inductance, through the MOSFET, and back. So that's your current loop. Okay. While that's happening, if you go over to the waveforms, on the I drain waveform, the current is beginning to ramp up. Now this current is going into the primary winding of the transformer, and the magnetic flux is building up, but it's not being coupled to the secondary because of these phase dots. This diode is blocking, so there's no current allowed to flow in the secondary winding. Therefore, the energy that's being created by the current ramp is being stored in the gap of the ferrite core. That's storing the magnetic flux energy. Okay. At the same time this is charging up, the C3 is providing output to keep this running. So that's why if you look at I out, you can see the current is dropping because it's supplying power to the grid during this charge cycle. Okay. As soon as you reach T1, the MOSFET switch, the PWM signal goes to zero. One of these pulses goes to zero, turns off the switch, and then instantaneously, if you look at the blue drain, you get this large spike. And the reason for that is at the time the switch turns off, the energy that's stored in the core in the gap begins to flow into the secondary. But this primary leakage inductance, it's not coupled. So this energy just begins to build up on the drain. Okay, so it manifests itself as this spike. And then at the same time, it's resonating with this drain capacity. So this leakage inductance and this drain capacitance form a resonant circuit. So not only is it peaking, but you're oscillating as well. Okay, that's the job of the snubber. So when the voltage rises above the level of V in, diode D1 becomes forward bias. It allows this energy to flow into the snubber resistance. Okay, and then dissipating it that way in the snubber resistance as heat. Okay, so now what happens is, as the current ramp, as we're now at T1 to T2, right? So now we've taken care of the spike, the snubber is doing its thing. So now the drain is sitting here at some voltage, some high voltage. Okay, and its energy is being sent to the secondary. Okay, and so C3 is charging up. So you can see ID2, and then you can see this I output is being fed by C3, which is being charged up. So that's why it's ramping up. Okay, and then when this current stops flowing, so all the energy's been dumped through D2, okay, and now what happens is this voltage that was sitting here now collapses, okay, and because of this drain capacitance, a resonance now is present, and therefore this voltage begins to oscillate. And this is a classic condition of a DCM, or a discontinuous mode. This is what happens. Because there's drain capacitance and you have that voltage there that's now no longer there, you have this oscillation. Okay, and this is between the primary L and the drain capacitance is causing that. Okay, so then eventually at T3 the cycle starts again. Okay, so the drain goes to zero because it's conducting. So that's the cycle. Next, we're going to look at simulation.